strike is the event of when a bird or a flock of birds collide with an airplane, and the result can make the airplane and the flight endangered and also the life of the bird. Sully is a movie that you have probably watched that is about an event of a bird strike, a famous event. The event happened when the Captain Sully and their crew uh, took off from an airport in New York, and in the process of taking off, they collided with a flock of birds, resulting in that made the airplane needed to emergency land, and it landed on the Hudson River. Miraculously, there were no casualties in that event. That event is actually based on a real-life event from the Captain Sullenberg that happened in 2009. There are statistics from the FAA, or the Federal Aviation Administration, that explains that in the range of 1990 to 2009, there were 229,000 bird strike events. That is approximately 1,500 bird strikes a year and 4 bird strikes a day. Airplane bird strike is a term to describe an airplane colliding with a bird or a group of birds, which can cause disruption to the aircraft and threaten the bird's safety. There have been many studies that have also tried to predict airplane failure using machine learning, some of which use MLP, SVM, linear regression, and random forests. Some problems that are still opportunities in the subject, among else, are imbalance problems and optimization. We did a systematic literature study on state-of-the-art airplane engine failure predictions. There are several researches. First, there is the general airplane engine failure, and this is done by Chelikmi et al. And in that research, they conducted general airplane engine failure with MLP and SVM, or support vector machine, and linear regression. And then there was the airplane remaining useful life, or RUL prediction, and this is by Liu et al. And Liu et al. Used logistic regression. And lastly, there was a research about engine fault prediction, and this was done by Yan et al. And Yan et al. Used random forest. And so for bird strike, this research area is still a research opportunity. We also studied about the state-of-the-art optimization by genetic algorithm feature selections around engine failures. First of all, there is the fault detection on induction machine bearings. This used genetic algorithm feature selection and was done by Gautama et al. And there was a genetic algorithm for balancing long short-term memory, or LSTM, and recurrent neural network, or RNN, on engine fault, and this was done by Chui et al. However, for genetic algorithm feature selection for bird strike prediction on airplane failure, this is still a research opportunity. So our research aim is to create an airplane failure prediction using a machine learning method optimized using genetic algorithm, or GA, feature selection. The GA here is to optimize the AUC, or for AUC maximization. The four machine learning methods are compared. Earlier we mentioned they are MLP, SVM, linear regression, and random forest. And for the imbalance, we use SMOTE for and G-main selection, and lastly we use GA with feature selection, or our novel method called ImbGAFS. So these are the papers that we are discussing in the related works. First of all, in the sector of airplane failure by bird strike, we found two state-of-the-art research by Nimagada and Misra et al. First, this is the research by Nimagada. It compared knife bias, KNN, and decision tree and found that knife bias is better than the other two. And then Misra also, Nimagada, used the FAA wildlife strike database, and it compared random forest and logistic regression and XGBoost and SVM and ANN and KNN, and found that random forest was the best of all of them. However, the Misra and Nimagada, although they used the FAA wildlife strike database, they did not point out that there was an imbalance problem in the dataset. So we moved on to other researches and we found out that we can use ROC threshold selection, AUC maximization, and also GA feature selection to improve our models in the matter if imbalance happens. So we read about Ojo's research and they use ROC threshold and ROC threshold in the research they found out that they can maximize the G-mean by using the best threshold in the ROC curve. And their study case was about fault detection in lithium-ion batteries. Also, Sadegi, they also use the same method, the ROC threshold selection, but their study case was on diabetes mellitus prediction. So we moved on to the AUC maximization, and we found two researches by Yan and Wang. First of all, Yan's research used AUC maximization with the use of a method called stochastic primal dual algorithm, which basically use stochastic gradient descent or SGD. And also Wang also used AUC maximization, but they use proximal SVM or PSVM, and they used it also for imbalanced data, like our case. And lastly, the GA feature selection was used by Alawat and Yang. Alawat used the GA feature selection to improve six machine learning methods, and it proved that it can improve ET, RDF, SBM, and also KNN, but it cannot improve logreg and it cannot improve PEG. And the research was about brain hemorrhage detection. And lastly, Yang research was also about feature selection. They used GA feature selection to select features that were extracted from a stream data. So this is our methodology. First, we obtain the airplane failure by bird strike dataset from Kaggle, and then we do dataset preprocessing. We use label encoders and other methods, and then we do prediction training using the four machine learning methods mentioned earlier. After that, we do ROC threshold selection with G-mean, and then the next step is to use GA to do AUC maximization, and lastly, we evaluate and we report our findings. So this is our bird strike dataset. It is from the Federal Aviation Administration. However, we downloaded the dataset from Kaggle. This dataset has 65,611 data items. It also has 18 features, one of which you can see here, and it has two labels. The output is the effect, and the labels there are two. The first label is the no damage or no damage caused, and the second label is cause damage or there are damage caused by the bird strike. So before we train the dataset with machine learning, we do pre-processing. Several steps in the pre-processing, among others, are searching for missing values and doing data imputation and then transforming categorical values. We found in our dataset there are 6,512 data items with missing values. We filled them with zero imputation. And then we found that 14 of our features are categorical values. We transformed them into numerical values with label encoder. So we have and compared four machine learning methods in this research. The first is support vector machine, or SVM. As the figure implies, the SVM separates two different labels in the feature space using a hyperplane. If the data is not linearly separable, the SVM uses a kernel trick. The kernel trick transforms the two-dimensional features into a higher dimension. By doing that, the SVM can use other types of hyperplanes to separate the data. In the kernel trick, there are several kernels that can be used. For example, there is the SMOTE, the radial basis function, or RBF, and lastly, there is the polynomial function. And then there is the MLP. The MLP is actually the formal form of the artificial neural network, or ANN. MLP explains that the ANN network is it consists of at least a input layer, an output layer, and several hidden layers. The minimum value of the hidden layer is 1. The MLP is constructed using iterations called epoch. In each epoch, the weights and the bias of each neuron is adjusted so it minimizes a loss function. The loss function is the difference between the predicted output and the actual output. And then there's the third method called logistic regression. Logistic regression transforms the data in the feature space again. If the data in the feature space has a linear correlation, then that linear correlation is then transformed with a logistic function. So each of the data is then tendentiously moved to one of the binary value. If not one, it is classed as a 0. And then lastly, the random forest is a type of ensemble learning method that processes the method called bagging. Bagging stands for bootstrapping and aggregating. Bootstrapping is the process of random sampling a dataset into several subsamples, and each subsamples are used to train a weak learner. A weak learner is a decision tree with limited capabilities. The final decision of the random forest is the aggregation of all weak learners. Usually, the method used for the aggregation is majority voting. So this is our optimal threshold selection algorithm. First, we collect several thresholds, sensitivities, and specificities from the ROC process using the soft labels and the actual labels. For each sensitivity and for each specificity, we calculate the G-mean using the following formula. And then lastly, we choose the most optimum threshold by using the argmax of the collection of G-means that we have collected in the process earlier. So this is the algorithm of our novel ImbGAFS objective function. First, we generate a random number. The random number has a range from 0 to 2 to the power of the number of features. This number is then converted into a binary number, and the binary number is converted into an array of Boolean values. This array of Boolean values is used to filter the original features into the new features called the sub-feature. Then we train our machine learning model, our optimal machine learning model using the sub-features, and then we optimize again the G-mean until we get the maximum value of our G-mean, and the G-mean value becomes the optimum value that is the output of our objective function, and that is the GA process. And before we did machine learning training, we did a Bayesian correlation analysis to observe the correlation between the features and the label. Here this is the heat map of the Bayesian correlation matrix. Here in the last row is the most important row. This is the correlation between the label, which is the effect indicated damage, with all the other features. Here we can see that the highest correlation is between the effect indicated damage with the effect impact to flight, which is 0.21. And also there are several features with low Pearson correlation value. Here you can see the lowest are record ID and also wildlife species, which is the species of the wildlife in the bird tribe. Several notable low features below 0.1. We can also find airport name, and there's also flight date, and there's also origin state, and there's also pilot born of birds or wildlife, and lastly there is the miles from airport. Some features have values between 0.1 and 0.2. Those features are the altitude bin, the aircraft make model, and there's also the aircraft number of engines, the aircraft airline operator, the wildlife size, and when, time of day, and feet above ground, and lastly the speed IAS in knots. We did standardization in our preprocessing before machine learning training because some of our machine learning models are sensitive to variable ranges between features. Standardization transforms a data's distribution if before it has a variable mean and standard deviation. After the standardization, the mean becomes 0 and the standard deviation becomes 1. In our case, our dataset has a mean value of 3008.1 and a standard deviation of 908.4. After our standardization process, the mean becomes 0 and the standard deviation becomes 1. And this is the result of our first test, which is the implementation of SMOTE and the machine learning models. So we cannot measure the machine learning models with accuracy because it does not describe the performance of a model when it is going through imbalance problem. Here we use ROC to compare the performance. In the left side is the models without SMOTE, and on the right side is the models with SMOTE. Here we can see that SMOTE increases the performance of logistic regression, SVM, and random forest. However, it does not increase the capabilities of MLP. Also, we can see that in both scenarios, we can see that random forest has the most optimum results, and the most optimum result of all of them is the random forest with SMOTE. So for the next step, we use random forest with SMOTE for our optimum model. Now we test the performance of the G-mean threshold selection. As we mentioned earlier, accuracy can be used to measure the performance of our random forest model. So here we use sensitivity and specificity. Sensitivity measures the performance of the majority label, and specificity measures the performance of the minority label. Here we can see before the threshold selection, there is a very high imbalance between the majority level performance and the minority level performance. The G-mean is the aggregation of both the sensitivity and specificity. In the first result, the G-mean is 0.5. After the threshold selection, we can see that the measurements are more balanced. Here we can see, although there is a decrease in sensitivity, the specificity increases around 4 times. The result is the G-mean, again, the aggregation of the both values increase from 0.5 to 0.8. This shows the success of the G-mean threshold selection process. Observing the objective function landscape is important to see how complex our problem is in the genetic algorithm in our ImbGAFS method. Here we can see a part of the objective function landscape. Here you can see that there are many values in this part of the objective function. The many values in the graph shows that there is a chance of getting trapped in local optimum. To avoid getting trapped in the local optimum, we need to increase exploration and decrease exploitation. In genetic algorithm, that can be done by increasing the probability of mutation and decreasing the probability of the parent genetics. So here we can see this is the result of the feature selection of our novel ImbGAFS. These are the feature names in the dataset of the aircraft bird strike dataset. And here are the Pearson correlation scores of each feature towards the label. And at the right side is the selection result of the ImbGAFS. Here we can see that the selection done by ImbGAFS does not take consideration the magnitude of the Pearson correlation. If it uses a threshold method, it will cut the features at a certain point. And this is a good choice. Why? Because by doing so with that stochastic type of method, you can see that the result of the ImbGAFS feature selection increases the performance of the AUC and also the sensitivity, the specificity, and lastly the G-mean. All of them increase from the result of the machine learning prediction from the previous random forest method. And here we discuss the results and point out our research contribution. So first, airplane failure detection by birdstrike have been previously done by previous research, but none of them take into consideration the imbalance problem in the dataset. Here we use some methods to find a solution for the imbalance dataset. Secondly, previous methods have used G-mean threshold selection, and some previous method has used AUC maximization. Here we use both of them to optimize the results of our machine learning model to get the best G-mean value. And lastly, we propose ImbGAFS, which is a novel GA feature selection. This method uses G-mean threshold selection as its objective function. Previous methods have used GA feature selection, but none of them have used G-mean threshold selection. And we prove that the use of ImbGAFS can improve the performance of failure detection by birdstrike. So this is our conclusion. First, we succeeded in implementing ImbGAFS, a novel feature selection method with G-mean selection objective function for datasets with imbalance problems. Then the imbalance problem in our research is moderate, where 6% of the dataset belongs to the minority label. Random forest is more optimum than MLP, SVM, and linear regression on airplane failure detection by birdstrike. And lastly, ImbGAFS improves the random forest G-mean value from 0.80 to 0.82. And that is the end of our presentation. Thank you for your attention. If you have any questions, let's do a discussion in the next session.